As an example of using persistence, we're gonna solve the point location problem using a persistent red-black tree, or essentially a persistent binary search tree. So this solution works as follows. Consider the sweep line algorithm for the line segment intersection. So let me go back to this algorithm. The algorithm is this one. And if you just think about the sweep line, the status of the sweep line, as we discussed, this is just a red-black tree, or essentially a binary search tree. So given at every point in time, the line segments that intersect with sweep line can be compared to each other, and they're stored in a binary search tree that only uses comparisons. So basically something like this, right? So we have this binary search tree that represents the segment stored intersected by the sweep line. We don't care about how this thing is stored or queried. What we care about here is how this is modified, because we want to remember all the versions or all these changes that are happening to this search structure. The modification happens in essentially all of these events. So when you have the top event, we insert S into the red-black tree. If it is bottom event, we remove S from the red-black tree, and over here we have the swap operation. And the swap operation can be obviously implemented with an insertion or deletion. So here we have just insertion, here we have a deletion, and we have both, right? So we have insertion and deletion. So at every event point, this data structure changes by insertion, deletion, or both. And assuming that we use a red-black tree, what we try to do here is that we want to turn this into persistence. We can essentially get this for free using the theorem, because remember that this is a tree. So if we look at every node, there is only one incoming pointer. And using the theorem, we can turn this partially persistent using a constant overhead in a space. What this means is the following, that if I want to change something, for example, imagine that I want to do a deletion followed by an insertion, right? So imagine that this node gets deleted, and then I insert another value into this tree. So now the tree looks like this. If this tree was ephemeral, then I would lose this information, and I would only have the latest updated version of it. But with persistent, we also keep this information, and we keep this information only using a constant amount of extra space, which is obviously optimal, right? Because we have to remember it, so it has to take some space. And in fact, what this allows me to do is that if I wanted to get to the blue red-black tree, I could essentially do it for free. It's not 100% for free, but I'm gonna explain what it means. But if I want to look at the updated blue tree, I could also get this piece of the blue plus this red, and so on. As more updates come, I could essentially get every single version of this tree in the past. Okay. So how can we use this? First, let's look at the analysis. In a red-black tree, the update time is log n. So we at most change log n pointers or log n nodes of the tree. We can keep the changes at a constant amount of space. So therefore, every update could only consume log n, or every insertion or deletion costs at most log n extra space in terms of overhead. Since we have n insertion and deletions, that means the total space is n log n. But if you look at the details of the red-black tree, which I'm not going to do, you can trust me on this, that the red-black tree can be rebalanced using only a constant number of rotations. This means that if you want to update a red-black tree, there are only a constant number of changes when it comes to changing the pointers and the contents of these nodes of a red-black tree. So therefore, an insertion or deletion only changes constant number of things. So therefore, it can be made persistent using only constant amount of extra space. So therefore, the total amount of space would be linear. The only thing that I haven't explained to you is how do we query this. And this is done as follows. So given this sweep line approach, we look at the events, right? So the start and the end point of the vertices are the events. Imagine that this is the time axis. So this is time. Mark the point in time when this changes occur. So here essentially time is x coordinate, right? So we're looking at the x coordinate of every line segment, this side the beginning x coordinate and the end x coordinate. And we mark these 2 points at the time. Then when a query comes with 2 points, so xq and yq, this xq is essentially a timestamp. We search in this one-dimensional input or in time. We find the time period in which this xq is between the 2 versions of the tree. So we find xq here, which gives you a value I here, or xi. What this means is that when the time was xi, we need to query this because this is the most updated. Actually, maybe in this case xi is this one. This is the most updated version of the tree at this point in time when it's relevant to the query. So using the persistent magic, we find the status of the sweep line at this point in time, which obviously includes all the line segments that are intersected by this vertical sweep line at the position when its x coordinate is equal xq. And here we're using the observation that if I look at 2 different timestamps, so let's say timestamp I and timestamp I plus 1, there is nothing interesting happening in between. So there is no event points. So therefore the combinatorial structure of this tree is essentially the same. So therefore I could use the red-black tree that exists at this point in time to query this point. So therefore by finding the predecessor of this query along this axis, I could find, for example, this line segment and this line segment. And as before, by following the face pointer of those edges, I could find the face that contains a query point. This essentially gives us the optimal solution for planar point location problem. It's an n log n space, n log n preprocessing time, linear space, and log n query time. But later we're going to see different solutions that exploit or exhibit different techniques that we need to learn in this course.